everyone. Today we're going to discuss about mass storage systems. Overview of mass storage structure. Magnetic disks provide the bulk of secondary storage for modern computer systems. Conceptually, disks are relatively simple. Each disk platter has a flat circular shape like a CD, and it looks like this. Common platter diameters range from 1.8 to 5.25 inches. The two surfaces of a platter are covered with the magnetic material. We store information by recording it magnetically on the platters. A read-write head flies just above each surface of every platter. The heads are attached to a disk arm, which is this one, that moves all the heads as a unit. The surface of a platter is logically divided into circular tracts, which are subdivided into sectors. The set of tracts that are at one arm position makes up a cylinder. There may be thousands of concentric cylinders in a disk drive, and each tract may contain hundreds of sectors. The storage capacity of common disk drives is measured in gigabytes. When the disk is in use, the drive motor spins it at a high speed. Most drives rotate 60 to 200 times per second. Magnetic tapes was used as an early secondary storage medium. Although it is relatively permanent and can hold large quantities of data, its access time is slow compared with that of main memory and magnetic disk. In addition, random access to magnetic tape is about 1,000 times slower than random access to magnetic disk, so tapes are not very useful for secondary storage. Tapes are used mainly for backup, for storage of infrequently used information, and as a medium for transferring information from one system to another. A tape is kept in a spool and is wound and rewound past in a read-write head. Moving to the correct spot on a tape can take minutes, but once positioned, tape drives can write data at speeds comparable to disk drives. Tape capacities vary greatly, depending on the particular kind of tape drive. Typically, they store from 20 to 200 gig. Some have built-in compression that can more than double the effective storage. Next one is disk structure. Modern disk drives are addressed as large one-dimensional arrays of logical blocks, where the logical block is the smallest unit of transfer. The size of a logical block is usually 512 bytes. The one-dimensional array of a logical blocks is mapped onto the sectors of the disk sequentially. Sector 0 is the first sector of the first track on the outermost cylinder. The mapping proceeds in order through that track, then through the rest of the tracks in that cylinder, and then through the rest of the cylinders from outermost to innermost. By using base mapping, we can convert a logical block number into an old-style disk address that consists of a cylinder number, a track number within that cylinder, and a sector number within the track. And now let's move on to the next topic, which is disk attachment. Computers access disk storage in two ways. First is the host-attached storage. It is a storage accessed through local I/O ports. These ports use several technologies. The typical desktop PC uses an I/O bus architecture called IDE or ATA. SCSI is a bus architecture, and it means Small Computer System Interface. Its physical medium is usually a ribbon cable with large number of conductors. Well, it's typically 50 or 60. SCSI protocol supports a maximum of 16 devices per bus. The devices include one controller card in the host, which is called SCSI initiator, and up to 15 storage devices, which is called the SCSI targets. FC is a high-speed serial architecture. FC means fiber channel. It can operate over optical fiber or over a 4-conductor copper cable. It has two variants. One is a large switched fabric having a 24-bit address space. This variant is expected to dominate in the future and is the basis of storage area networks or the SANs, which will be discussed later. The next one is network attached storage. It is a special purpose storage system that is accessed remotely over a data network. The figure shows itself. Clients access network attached storage via remote procedure call interface such as NFS for Unix systems or CIFS for Windows machines. The remote procedure calls are carried via TCP or UDP over an IP network. It is usually the same local area network that carries all the data traffic to the clients. Network attached storage provides a convenient way for all the computers on a LAN to share a pool of storage with the same ease of naming and enjoyed with local host attached storage. However, it tends to be less efficient and have lower performance than some direct attached storage options. Storage area network. A storage area network is a private network connecting servers and storage units as shown in the figure. The power of SAN lies in its flexibility. Multiple hosts and multiple storage arrays can attach to the same SAN, and storage can be dynamically allocated to hosts. A SAN switch allows or prohibits access between the hosts and the storage. As one example, if a host is running low on the disk space, the SAN can be configured to allocate more storage to the host. SANs make it possible for clusters of servers to share the same storage and for storage arrays to include multiple direct host connections. Disk scheduling. One of the responsibilities of the operating system is to use the hardware efficiently. For the disk drives, meeting this responsibility entails having fast access time and large disk bandwidth. The access time has two major components. First, the seek time is the time for the disk arm to move the heads to the cylinder containing the desired sector. Secondly, the rotational latency is the additional time for the disk to rotate the desired sector to the disk head. The disk bandwidth is the total number of bytes transferred, divided by the total time between the first request for service and the completion of the last transfer. We can improve both the access time and the bandwidth by managing the order in which disk I/O requests are serviced. First come, first serve scheduling. This algorithm is fair, but it generally does not provide the fastest service. Consider the example in front. A disk queue with requests for I/O to blocks on cylinders in that order. If the disk head is initially at cylinder 53, it will first move from 53 to 98. Why? Because 98 is next on the queue. Then to 183. Next is 237, 122, 14, 124, 65, and 67. So, it just basically follow the queue on the rule. Shortest seek time first scheduling. This algorithm selects the request with the least seek time from the current head position. Since seek time increases with the number of cylinders traversed by the head, SSTF chooses the pending request closest to the current head position. For the example, the closest request to the initial head position, which is 53, is at cylinder 65. Once we are at the cylinder 65, the next closest cylinder is 67. From there, the request at cylinder 37 is closer than the one at 98, so 37 is served next. Continuing, we service the request at cylinder 14, then 98, followed by 22 rather. Next is to 124, and finally 183. This scheduling method results in a total head movement of only 236 cylinders, little more than one-third of the distance needed for first-come first-served scheduling of this request queue. Clearly, this algorithm gives a substantial improvement in performance. Shortest seek time first scheduling is essentially a form shortest job first scheduling. It may cause starvation of some requests. Remember that requests may arrive at any time. Scan scheduling. In this algorithm, the disk arm starts at one end of the disk and moves toward the other end, servicing requests as it reaches each cylinder, until it gets to the other end of the disk. At the other end, the direction of the head movement is reversed, and servicing continues. The head continuously scans back and forth across the disk. The scan algorithm is sometimes called the elevator algorithm, since the disk arm behaves just like an elevator in a building. First servicing all the requests going up, and then reversing to service requests the other way. For the example, we need to know the direction of head movement in addition to the head's current position. Assuming that the disk arm is moving towards 0 and that the initial head position is again 53, the head will next service 37 and then 14. At cylinder 0, the arm will reverse and will remove toward the other end of the disk, servicing the requests at 65, 67, 98, 122, 124, and 183. If a request arrives in the queue just in front of the head, it will be serviced almost immediately. A request arriving just behind the head will have to wait until the arm moves the end of the disk, reverses direction, and comes back.
Scan, or circular scan. It works like the elevator to some extent. It begins its scan toward the nearest end and works it all the way to the end of the system. Once it hits the bottom or top, it jumps to the other end and moves in the same direction. So when it reaches the other end, it immediately returns to the beginning of the disk without servicing any requests on the grip. Consider a season scheduling with queue 98, 183, 37, 122, 14, 124, 65, and 67. The head starts at 53, then goes to 65, 67, 98, 122, 124, 183, and 129. After it reaches the other end, it will go to its other end also, which is 0. And as we notice, it didn't cater 14 because first, before it will cater other requests, it will first jump to its other end. So it went to 0 and cater 14 and 37. The advantages of C-scan scheduling is that it is better than scan scheduling in terms of waiting time because it provides uniform waiting time. C-look is an enhanced version of C-scan. In this scanning, it doesn't go past the last request in the direction that it is moving. The arm only goes as far as the last request in each direction, then reverses direction immediately without first going all the way to the end of the disk. For example, the last request in this figure is 183, so it only went to 183, it doesn't go to 199. And after it reaches 183, it directly go to 14 and process other requests. Booting from a disk in Windows 2000. The Windows 2000 system places its code in the first sector on the hard disk, which is the master boot record or the MBR. It allows a hard disk to be divided into one or more partitions. In Windows 2000, it allows a hard disk to be divided into one or more partitions. So in this example, we have 4 partitions: partition 1, 2, 3, and 4. One partition, identified as the boot partition, it contains the operating system and device drivers. Booting begins a Windows 2000 system by running code that is residing in the system's ROM memory. This code directs the system to read the boot code from, and this MBR, it contains a table partition or a partition table, and a boot code. For the hard disk and a drive, and a flag indicating which partition the system is to be booted from. So once the system identifies the boot partition, it reads the first sector from that partition, which is the boot sector, and it will continue with the remainder of the boot processes that includes loading the various subsystems and system services. Data structures for swapping on Linux system. Linux is similar to Solaris in that swap space is only used for anonymous memory or for regions of memory shared by several processes. Linux allows one or more swap areas to be established. A swap area may be in either a swap file on a regular file system or a raw swap partition. Each swap area consists of a series of 4 kilobytes page slots, which are used to hold swapped pages. Along with each swap area is a swap map. It is an array of integer counters which corresponds to a page slot in the swap area. If the value of a counter is 0, the corresponding page slot is available. Values greater than 0 indicate that the page slot is occupied by a swapped page. The value of the counter indicates the number of mappings to the swapped page. For example, a value of 3 indicates that the swap page is mapped to 3 different processes. Which can occur if the swap page is storing a region of memory shared by 3. RAID. RAID stands for Redundant Array of Inexpensive Disks. It is a technology that is used to increase the performance or reliability of data storage. It is also a multiple disk drives that provides reliability via redundancy. Reliability via redundancy means that we store extra information that is not normally needed but that can be used in the event of failure of a disk to rebuild the lost information. So even if a disk fails, data are not lost. The simplest approach to introducing redundancy is to duplicate every disk. This kind of technique is called mirroring. In this mirroring, every write is carried out on both disks. If one of the disks fails, the data can be read from the other. So data will be lost only if the second disk fails before the first failed disk is replaced. Numerous schemes to provide redundancy at lower cost by using the idea of disk striping combined with parity bits have been proposed. These schemes have different cost-performance trade-offs and are classified according to levels called RAID levels. RAID level 0, which is striping. In this level, system data are split up in blocks that get written across all the drives in the array. There is no redundancy, and the disadvantage of this, if one drive fails, all data in RAID 0 array are lost. As we can see in this example, the system data are being split up in blocks, block 1, block 2, block 3, 4. So there is no redundancy that occur here, and if this drive fails, all data in this array will be lost. RAID level 1, which is mirroring. In this level, data are stored twice by writing them to both the data drive and a mirror drive. If a drive fails, the controller uses either the data drive or the mirror drive for data recovery and continuous operation. In this level, we will need at least 2 drives for a RAID 1 array. RAID level 5. This is what the most common secure RAID level, which is striping with parity across drives. It requires at least 3 drives but can work with up to 16. Data blocks are striped across the drives, and on one drive, a parity checksum of all the block data is written. Parity data are not written to a fixed drive. They are spread across all drives. RAID 5 can withstand a single drive failure without losing data or access to data. RAID 6. Striping with dual parity across drives. It is much like RAID level 5 but stores extra redundant information to guard against multiple disk drive failures. Instead of parity, error correcting codes such as the Reed-Solomon codes are used. In this scheme, 2 bits of redundant data are stored for every 4 bits of data compared with 1 parity bit in level 5, and the system can tolerate 2 disk failures. RAID level 1 plus 0 or mirroring plus striping. In this level, it provides security by mirroring all data on secondary drives while using striping across each set of drives to speed up data transfers. If something goes wrong with one of the disks in a RAID 10 configuration, the rebuild time is very fast since all that is needed is copying all the data from the surviving mirror to a new drive. In RAID level 0 plus 1, if a single disk fails, the entire stripe is inaccessible, leaving only the other stripe available.
Stable storage implementation. We introduce write-ahead lag, which requires the availability of stable storage. In order to implement a stable storage, we need to replicate information in more than one non-volatile storage media with independent failure nodes. We also need to update information in a controlled manner to ensure that we can recover the stable data after any failure during data transfer or recovery.
Tertiary storage devices. Low cost is the defining characteristic of tertiary storage. Generally, tertiary storage is built using removable media. The common examples of removable media are floppy disks and CD-ROMs. There are also other types of removable media that is available. The following are the examples of removable disks.
There's another kind of removable disk, which is the magneto-optic disk. Magneto-optic disk records data on a rigid platter coated with magnetic material. Although it's a magnetic disk, its recording technology is quite different. In MO disk, the MO head flies much farther from the disk surface than a magnetic disk head does, and the MO's magnetic material is covered with a thick protective layer of plastic or glass. Because of this arrangement, it makes the disk much more resistant to head crashes. Therefore, there is a large, weak magnetic field that can record a tiny bit. MO disk drive has a coil that produces a magnetic field. To write a bit, the disk head flashes a laser beam at the disk surface. Now, the laser is aimed at a tiny spot where a bit is to be written. So the laser hits this spot, which makes the spot vulnerable to the magnetic field. Laser light is used to read data in magneto-optic. Another kind of removable disk is the optical disk. Optical disks do not use magnetism at all. Instead, they employ special materials that are altered by a laser light to have dark or bright spots. Example of optical disk technology is the phase change disk. Phase change disk is coated with a material that can freeze into either crystalline or amorphous state. It also uses laser light at 3 different powers: low power to read data, medium power to erase disk, and high power to write to the disk. On the other hand, worm disks
or write once, read many times, can only be written once. Worm disks have thin aluminum film sandwiched between two glass or plastic platters. To write a bit, the drive uses a laser light to burn a small hole through the aluminum. It's possible to destroy the information on a worm disk by burning holes everywhere, but it's impossible to alter the data. Because the metal layer is encapsulated between the protective glass or plastic platters, and also the magnetic fields cannot damage the recording, worm disks are considered as durable and reliable. The latest Write Once technology records on an organic polymer die instead of aluminum. The die absorbs laser light to form marks. It is used in recordable CDR and DVD-R. If there are read-write disks and worm disks, there's also read-only disks. Read-only disks come from the factory with the data pre-recorded. It uses technology similar to that of worm disks, but bits are pressed and not burned. It is also considered as very durable. Another type of removable medium is the magnetic tape. Magnetic tape has similar transfer rates with disk drives but holds more data. Its random access is also slower because magnetic tape requires fast-forward or rewind operation. One of its pros is that it's less expensive compared to disk drive with equivalent capacity. Large tape installations use robotic tape changers that move tapes between tape drives and storage slots in a tape library. It provides the computer automatic access to many tape cartridges. The robotic tape library has lessened the overall cost of data storage. If a disk resident file is not needed, it can be archived to tape for a lower cost per gigabyte. If the file is needed in the future, the computer can stage it back into disk storage for active use. Robotic tape library is sometimes called nearline storage because it is between high performance of online magnetic disks and the low cost of offline tape. A library that holds few tapes is called a stacker, and a library that holds thousands of tapes is called a silo. There are two major jobs of an operating system, and these are to manage physical devices and to present a virtual machine abstraction to applications. For hard disks, the OS provides two abstractions. One is the raw device, which is an array of data blocks, and the other is the file system in which the OS queues and schedules the interleaved requests from several applications. For hard disks, the OS provides two abstractions. One is the raw device, which is an array of data blocks, and the other is the file system in which the OS queues and schedules the interleaved requests from several applications. In handling removable disks, most operating systems handles them almost exactly like non-removable disks. So when a new cartridge is mounted into the drive, it must be formatted and then an empty file system is generated. Unlike disks, tapes are handled differently. When tapes are inserted, they are presented as a raw storage medium. An application does not open a file on the tape. Instead, it opens the whole tape drive as a raw device. Usually, the tape drive is reserved only for that exclusive use of that application. And of course, when the tape drive is presented as a raw device, the OS does not provide file system services. Therefore, the application must decide on how to use the array of blocks. The only problem from this way of using tape is that since every application makes up its own rules for how to organize a tape full of data can generally only be used by the tape drives have different set of basic operations. Instead of seek, a tape drive uses the locate operation. The tape locate operation is more precise than the disk seek operation. It positions the tape to a specific logical block and not an entire track. The read position operation returns the logical block number where the tape head is, and the space operation enables relative motion. In writing a block on the tape drive, it has the side effect of logically erasing everything beyond the position of the write. On account of this side effect, Most tape drives are append-only devices because updating a block in the middle of the tape also effectively erases everything beyond that block. In addition, the tape drive places an EOT mark after the block that is written. Another operating system issue is file naming. The issue of naming files on removable media is especially difficult when we want to write data on a removable cartridge on one computer and then use the cartridge in another computer. If both machines are the same type and have the same kind of removable drive, the only difficulty is knowing the contents and data layout on the cartridge. But if the machines or drives are different, many additional problems can arise. Even if the drives are compatible, different computers may store bytes in different orders and may use different encodings for binary numbers and even for letters. Today's operating systems generally leave the namespace problem unsolved for removable media and depend on applications and users to figure out how to access and interpret the data. Fortunately, few kinds of removable media, such as the CD, are so well standardized that all computers use them the same way. DVD formats are also well standardized. The last operating system issue is the hierarchical storage management, or HSM. A hierarchical storage system extends the storage hierarchy beyond primary memory and secondary storage to incorporate tertiary storage. Tertiary storage is usually implemented as a jukebox of tapes or removable disks. Usually, incorporating tertiary storage is by extending the file system. Small and frequently used files remain on disk, while large, old, and active files are archived to the jukebox. The jukebox referred here is the robotic jukebox. A robotic jukebox enables the computer to change the removable cartridge in a drive without human assistance. The major uses of this technology are for backups and hierarchical storage systems. HSM is usually found in supercomputing centers and other large installations that have enormous volumes of data that are used seldom, sporadically, or periodically. Next, we'll proceed to the performance issues. There are three most important aspects of tertiary storage performance, and these are speed, reliability, and cost. First, we'll talk about speed. The two aspects of speed in tertiary storage are bandwidth and latency. In measuring bandwidth, we use bytes per second. The sustained bandwidth is the average data rate during a large transfer. That is the number of bytes divided by the transfer of time. And the effective bandwidth calculates the average over the entire I/O time, including seek or locate and any cartridge switching. The sustained bandwidth is the data rate when the data stream is actually flowing, while the effective bandwidth is the drive's overall data rate. The second aspect of speed is the access latency. Access latency is the amount of time needed to locate data. The disk access simply moves the arm to the selected cylinder and waits for the rotational latency, which may take less than 5 milliseconds. On the other hand, access on tape requires winding the tape reels until the selected block reaches the tape head, which can take tens or hundreds of seconds. So, we can generally say that random access within a tape cartridge is kind of 1,000 times slower than random access on disk. The reason of the low cost of tertiary storage is because of having many cheap cartridges share a few expensive drives, and the removable library is best devoted to the storage of infrequently used data, because the library can only satisfy a relatively small number of I/O requests per hour. Even though we often think good performance means high speed, another important aspect of performance is reliability. A fixed disk drive is more reliable than a removable disk or tape drive. This is because Removable storages are more likely to be exposed to harmful environment conditions. And an optical cartridge is considered more reliable than a magnetic disc or tape because the layer that stores the bits is protected by a transparent plastic or glass layer. There is one weakness of a fixed magnetic disc. A head crash in a fixed hard disk generally destroys the data, whereas the failure of a tape drive or optical disk drive often leaves data cartridge unharmed. Storage cost is another important factor. Main memory is much more expensive than disk storage. The cost per megabyte of hard disk storage is competitive with magnetic tape if only one tape is used per drive. The cheapest tape drives and the cheapest disk drives have had about the same storage capacity over the years. Tertiary storage gives a cost savings only when the number of cartridges is considerably larger than the number of drives. In this graph, the cost of DRAM fluctuates widely. In the period from 1981 to 2004, we can see the three price crashes around 1981, 1988, and 1996 as excess production cost and oversupply in the marketplace. We can also see two periods around 1987 and 1993 where shortages in the marketplace caused significant price increases. This graph shows the hard disk price from 1981 to 2008. In the case of hard disks, the price decline has been steadier. And in this graph, it shows the cost of tape drives throughout the years. Tape drive prices also fell steadily up to 1997. Since 1997, the price per gigabyte of inexpensive tape drives has ceased its dramatic fall. Although the price of mid-range tape technology has continued to fall and is now approaching that of the inexpensive drives, tape drive prices are not shown for years prior to 1984. We can see from these graphs that the cost of storage has fallen dramatically. By comparing the graphs, we can also see that the price of disk storage has plunged relative to the price of DRAM and tape. So guys, this is the end of chapter 12, which is about mass storage systems. We hope you learned something from us, and thank you all for watching.